We have already discussed the uniform random variable. Okay, we derived stated the probability density function. We also derived the cumulative distribution function. Then we derived the expectation. Then we derived the variance and also coefficient of variance. So these are the standard things that we look upon when we talk about random variables. So now there are two more random variables which are very important. We will try to understand those two things. One is the exponential. Usually it's called as exponentially distributed random variable, and the third is the Gaussian or normal random variable. For each one of these, we will try to look at the density function, distribution function, and the expectation, variance, and so on. So the exponential random variable. Okay. So let's say x is an exponentially distributed random variable. What do we mean by that? It has one parameter. You can use any symbol to denote it. We conventionally use the symbol lambda. And this is a non-negative random variable. So it doesn't take negative values. It always takes only non-negative. Zero can be taken, zero or positive. So it's a non-negative continuous valued random variable. That is one of its properties. And if only if you specify its parameter lambda, then everything can be known about this random variable. That is why it is called as the parameter. That is, by having different values of lambda, we can generate different exponentially distributed random variable. So we define, we say a random variable as exponential distribution if its probability density function has an exponent term in that. Okay. So, but it has to be normalized. So if we say it is e power of something, a power of something, anything it can be that, we take it as the e power of some, where the variable should be sitting on the top. Okay, as an exponent. You may also have a character, this one, what is called as the multiplying factor to that x. Okay. So then it has an exponential factor in the density function. If you have a constant, okay, ax plus y and so on, e power of minus y can be taken, which is again a constant, which can be brought in. So when we say exponentially distributed, it has to be in the form e power of something, where x should be there. For it to be normalizable, it has to be minus only, it will be minus ax or lambda x or something like that. If it is plus, as x increases, because it can take non-negative values up to infinity, it will not be normalized. So the density function, which we will write it like this one, takes the form lambda e power of minus lambda x for x greater than or equal to 0 and 0 otherwise. So this is how the density function, probability density function of an exponentially distributed random variable will look. So again we will have a notation for it. When we say we want to tell that x is exponentially distributed, we will write it like this. exp or expo depending upon the taste of those who define it. But when you write it like this, it has to be understood that x is defined to be an exponentially distributed random variable with a parameter lambda. Then automatically it means that its density function will have this. So for x less than 0, the density function is 0, which means that the probability of it taking negative values is 0. So it cannot take any negative values. That is what we mean. Probability is 0 means it can take some value, but its probability is 0 means it will not take. And it can take all possible non-negative values, 0 onwards. And whose probability density is given. This is not probability, but probability density is given. What does it mean? Probability that x lies in a small interval x and x plus dx is nothing but fx of x dx. This is the interpretation of the probability density function. Okay, you will never tell that p of x equal to x is equal to and so on. That is p of x equal to x can be given some value if it is a discrete random variable. Whereas similarly, for a continuous valued random variable, you cannot write like this. This is always 0. So the only thing that can be defined is you have to specify an interval, and we can ask the question, what is the probability that the random variable will take a realization in that interval? For every given interval, you can compute it. Even negative, positive, all this, it may be 0, but you can always find it. But how to interpret the density? If you take an interval of very small size, then the density will give you, actually in literal sense, it is the density of the concentration of the probability. To get the actual probability, you will multiply it by the interval. So density times this, because it is one dimension, there is no volume, it's a one dimension. So you have to multiply interval size. That will give you the probability. So this is how we will always interpret. So first, is it normalizable? That can be checked by integral minus infinity to plus infinity fx of x dx to be equal to 1. So here what happens is that the random variable takes value only starting from 0. So the lower limit has to be 0 in integration, because up to 0 anyway it is 0, those integration will not contribute anything. So it is 0 to plus infinity, and you plug in this value, this expression for the density in this one, and this has to be obeyed. So you just find what it is. So it is lambda into this one, that is e power of minus lambda x by minus lambda between 0 and infinity. So you will get this goes away, so you will get minus 1 into, if you substitute infinity, e power of minus infinity is 0 minus x, if you substitute it is 0, e power of 0, 1. Get it. So what do you get? You get 1. So the density function is normalized. Therefore, it is a valid probability density. So this is true for every random variable. These are well-known random variables, so it is defined. If you are told that we define a random variable x whose density function is of this one, okay, and then if you are asked whether it is valid, the first thing you have to do is to check whether the density function is normalizable, whether it is a valid density function. To do that, we have to do this process and then check whether it is valid. Now we can see why we are having a prefactor of lambda here. Only if it is a lambda, it becomes normalizable. That is why we are putting a lambda here. Everything follows one. We say it is exponentially distributed. By that we mean it has to be of this form. Okay, x has to be on the top, then only it will be exponentially distributed. Negative because it has to be normalized. And you can have any constant here, not just lambda plus a plus b into x, ax plus b, and all you can have. but ax will remain here and e power of b will be absorbed to the constant. Okay, and here that a is what we are calling now as the lambda. Everything follows like that. But whatever may be the prefactor, we call this as the exponent, this is the prefactor, should be such that it has to be normalized. Therefore, lambda is the only thing which normalizes it. So we are using this. Now, what is the u? Why are we interested in this? Exponentially distributed random variable can be used as a model for the arrival time of an event. That is, you start waiting at a time, arbitrary time, you call time t is equal to 0, and then wait for an event to occur. How much time it takes for the event to occur? That time interval can be modeled as an exponentially distributed random variable for many naturally occurring events. For example, waiting for an arrival of a customer to a shop, or arrival of a taxi to a taxi stand, or a lifetime of a component. Okay. So the situation is that is what we saw in Poisson random variable. We have an infinite population from which events can occur. Many entities occur. Each one of these entity can give rise to an event, and each entity gives rise to an event in a manner which is independent of other entities. So now we are looking at events. So at given time you start waiting for the event to occur. You start measuring the time at an arbitrary time, set it to be t is equal to 0, and then look for the time it takes until the event has occurred. And that time can, at many times, can be modeled as an exponentially distributed random. That is why we are doing. For example, the lifetime of a component. You have a bulb here, or a fan, or whatever it is. So you start putting it to use, and then you would like to look at the lifetime of the component of this one when it fails. Okay. So that depends upon the manufacturer's ability to make it more reliable and so on. But whatever it is, you can model, you can tell that it is on the average work for 5 years, so that is why you will give a 5-year warranty and so on. But that does not mean on the 5th year it will break down. It may go before that, or it may go after that and so on. And the actual time it takes, if you take thousands of that and then look at the actual lifetime of all those 1,000 fans, and then what you do is it may, and then the granular, you can get time, you can segregate it in terms of months, because the exact days or something like that. So maybe if you put it in this month, and then how many have failed in this one, how many have failed in this one, if you look at this one, and that can be exponentially distributed. That lifetime of the component can be exponentially distributed. So that is what this distribution stands for, and it is useful. So we have looked at this one thing. What else are important? Yeah. To get a feel for how is it, how will this look like if you plot X, the realizations of the capital X, against fx of x. If you plot it, how will it look like? So when x equal to 0, but negative it is 0. So all these are zeros only. So it will be like this, and then it will become positive. For x equal to 0, then what will happen? This factor is 1. You will have lambda. So at x equal to 0, you start from a place which is lambda. The height of this one will be lambda. After that, if you look at as x increases, this is a decaying function, in the sense that it will always be, it will reduce, and therefore the overall thing has to reduce. And it is exponentially decaying, slowly decaying. And when it will become 0? Only when x equal to infinity. When x becomes plus infinity, e power of minus lambda infinity is 0, then it becomes 0. So it will become 0 only here So it will be something of this type. So this is why this is for a particular lambda, this is how the PDF will be. Now, as lambda changes, how will it change? So let us take 3 values of lambda which are distinct like this one, and let's look at how the function will look like for different values of lambda. Lambda 1 is larger, lambda 2 smaller, and so on. So if you again, it is 0 up to this point for all of them, and then for a curve corresponding to this one, you will start from lambda 1. For a curve corresponding to, you will start from lambda 2, and here it will start from lambda 1. And all of them are going to be decaying. Number 1. Number 2 is that all of them are normalizable, in the sense that you find the so the area under this curve has to be equal to 1. So if you look at this one, it is starting from lambda 1 and then it is decaying as lambda 1 e power of minus lambda 1. Yes. Here lambda 1 is larger, which means that the decay rate is larger as compared to the other. So it will decay faster. So if you let us just plot it. Then it will be of this form. Compared to this, how will this curve with the parameter lambda 2 look like? It has to start from here. And it will decay with a rate which is lambda 2 e power minus lambda 2x. And this is lesser than this. So it will decay a little slower than this. So in long time, if you look at this one, its decay is slower, so it will be above this. And it has to be normalizable. The area under both these curves has to be same. Now, if you start from this and then it cannot increase, it has to only decrease. You go like this one. The area under both these curves has to be same. Already this has taken over the race. It is higher. So it has to compensate. Which means that this has to sometime cross over and then become like this. If you look at lambda 3, again still more details, start from lambda 3 and all of them should have the same area. So again, it should go like this. So this is how the density function of the exponentially distributed number is. Then the cumulative distribution function. And fx of x is what we will denote, and again by definition it is probability that x is less than or equal to x, and it can be obtained from the density function. Use the standard formula. What is it?